Hello everyone. We're now learning of the different ways to test for heteroscedasticity. In the previous video, we reviewed the Bruce-Pagan test for heteroscedasticity, where the goal is to look for the relationship between the error term and the x values. So we do a regression of u hat square on all of the x variables, and we look for joint significance of each of those slope coefficients. If there is evidence to reject the null, then we go ahead and reject the null and conclude that there is heteroscedasticity in the model. If there is no evidence to reject the null, in that case, we don't, then we go ahead with the story that there is homoscedasticity in the model. So the underlying process is that we regress the u hat square on all of the x variables because our goal is to see if the u hat square varies with the x values. So this was the Bruce-Pagan test, and we reviewed a couple of examples as well. Now, using a similar line of reasoning, we have another test coming from the econometrician White, and the test is named after him. It's called the White test. So we're going to regress u hat square on all of the x variables. In addition to just the x variables, we're going to also add the squares and cross products of the different x variables into our regression equation. So for example, if we have three regressors in our model, x1, x2, and x3, the White test will involve us running a regression of u hat square on x1, x2, and x3. It will also include the squares of each of these regressors in the regression model. So we're going to have additional terms for x1 square, x2 square, and x3 square. And we're also going to include the cross products of these regressors. So x1, x2, x2, x3, and x1, x3. Those will be three more interaction term regressors that we'll add into our regression. So we're going to regress u hat square on all the x variables, their squares, and the cross products. And now the test for heteroscedasticity is that our null hypothesis will be the joint, will be testing for all of these delta coefficients, right? All the coefficients running from delta 1 to delta 2 to delta 3 and so on up to delta 9. All of these slope coefficients are jointly 0. That will be our null hypothesis. So we could test this null hypothesis using an F test, we could use an LM test. The process is the same as before. I mean, the way in which we conclude whether we reject the null or don't reject the null, the F and LM statistic, the test works in a similar way as we saw earlier. The only caveat here is that when you do this version of the F test, there are a lot more regressors that you have in your regression model, in your u hat square regression. The more regressors there are, the more parameters to be estimated. So this just starts causing a degrees of freedom problem. So you need a sample size that is at least as large as the number of coefficients that you need to estimate. So if we have more regressors, then that's just going to cause a lot more coefficients to be estimated. And generally, economists tend to like higher degrees of freedom than lower degrees of freedom. So for example, if you have 6 regressors, right, it means you're going to have 27 different parameters to be estimated. So with six regressors, you will have 6 regressor terms plus another 6 for just the squares. And then you will have 6 C2 cross product terms. So that will be what, another 15 cross product terms. So you'll just have 27 different covariates along with an intercept that you need to be 27 slope parameters and an intercept to be estimated. And that's just a lot of parameters. So there's an alternate version of the White test that exists, which uses a very simple intuitive logic. Now, when you run a regression of y on x, right, and if you want to go and predict your y values, the y hat values are just predicted from this particular expression, right? It comes from your the regression equation that you fit. Beta naught hat plus beta 1 hat times your x1 and so on up to beta hat k times your xk. So we can get the predicted values once we have the regression. Now these fitted values or the predicted values are all a linear function of your x variables. So if I take this predicted value and if I square both the sides, I'll have y hat square on my left-hand side. And the particular expression that I see get on the right-hand side will include squares and cross products of the x variables. So think of it simply like this, right? If you have y is equal to, a plus bx1 plus bx2, the whole square. When you take a square of that right-hand side expression, you're going to have squares of the x variables as well as the cross products there. So instead of including every single replacer, its squares and its cross products, all I can do is just include the y hat and y hat square, because y hat and y hat square are implicitly linear functions of the x variables, their squares and the cross products. So if I run the white test in this manner, then all that I'll have to do is I'll regress u hat square on my predicted y hat and my y hat square and use that as the basis for my test, for testing for heteroscedasticity. So this way, I still retain the essence of saying that u hat square is now a function of the x's, their squares, and the cross products. But now I also save on the degrees of freedom because now I only have to estimate an intercept and two slope coefficients. So this version is just an alternate form of the white test. So here, to test for heteroscedasticity, my null hypothesis is that u hat square doesn't depend on any x variables. So delta 1 and delta 2 are jointly 0. That will be my null hypothesis. I could construct an LM test statistic for this. I could also do an F test. And the way we interpret those statistics works in the same way as it usually does. So for a particular example that we've been looking at, turns out the p-value from the LM test is about 0.178. That's a large p-value. So there's no evidence to reject the null. So we conclude that there is no heteroscedasticity. There's no evidence for heteroscedasticity in this data set. So that's another way of testing for heteroscedasticity. So that brings this section to a close. In the next set of videos, we're going to cover another method of accounting for this heteroscedasticity issue called the weighted least squares method. So I'll see you in that video.